Hello and welcome to this Icarus presentation. My name is Katrina Dupuyer and I work for the engineering consultancy Research Driven Solutions, who are based in Dublin, Ireland. The topic that I will be presenting today is resilience, resilience assessments, and climate change adaptation. Icarus is a Cedar-funded project with the primary objective of improving the uptake of climate change adaptation in the decision-making processes of road authorities. In this project, we follow 6 stages as shown on the slide below. Firstly, we have framing and business as usual stages. Then we have adaptation options, looking at what could we do, what can we implement. Then we have the decision stage where we try to decide what we can do. We then move on to implementing our adaptation options. And the final stage is the monitoring and evaluation stage, looking at what we learned and how have we progressed. In this video, we will focus on the first 2 stages, which are framing and business as usual, where we will look at ways to assess how we do things now. In this video, I will introduce the concept of resilience and ways to assess infrastructure resilience. I will also introduce the concept of a resilience impact score, which was developed for this project. And I will show how resilience may be used to provide input in decision making and assessment of possible adaptation strategies. Most of us are familiar with some definition of resilience, and it can be used to relate to physical, social, or economic systems. Thinking about how we might define resilience, we normally consider how a person or a system would respond to a damaging event and carry on or continue to provide service through the event or after the event happens. In 2007, Bruno first presented the 4 R's of resilience, which are widely used. These are robustness, redundancy, resourcefulness, and rapidity of response. So these incorporate how robust your system is physically. Are there redundancies, say in a transport network? Are there other ways to travel? How resourceful is the system? Are there financial or are there human resources available to respond to the event? And how quick does that response come, the rapidity of response? So these are thought to encompass all the aspects, really, of the definition of resilience. The definition we have chosen to use for the Icarus project is the IPCC definition, which is as follows. The capacity of social, economic, and ecosystems to cope with a hazardous event or trend or disturbance, responding or reorganizing in ways that maintain their essential function, identity, and structure, as well as biodiversity in the case of ecosystems, while also maintaining the capacity for adaptation, learning, and transformation. Let's look at that in a little more detail. It's important to note here that this definition highlights the ability of a system to maintain its essential function while also maintaining capacity for adaptation, learning, and transformation. So resilience is basically defined as the ability of a system, social, economic, or physical, to maintain service if a disruptive event occurs, but also have the potential to adapt to future events. And this is what gives it a temporal aspect. In this project, we studied 2 ways to assess the system's resilience, which are the resilience triangle and the response curve, and these are widely published in the literature. The first way that we assessed was to assess the system's response over time, which can be done using a resilience triangle as shown. Quality of infrastructure or functionality is shown on the y-axis, with time on the x-axis. In this case, an event occurs at time equal to t0 when the system's performance drops to point B. The system's performance is then monitored as the system recovers to full functionality or service at time is equal to t1. The second way to assess the resilience is to use a response curve. In this way, the expected recurrence time of an event combined with the likely damage or disruption of a system are assessed. The resilience can then be quantified by the area under the curve. For the Icarus project, we chose to use the resilience triangle, adapted from Tierney and Bruno as shown here. We have quality of infrastructure or functionality on the y-axis and time on the x-axis. An event occurs at time t0, which causes a drop in quality or functionality. Over time, with repairs, full functionality may be restored by time t1. This may look different for other systems, where the system may never return to full functionality, or indeed functionality is enhanced and the system returns to a higher level of functionality than before, above 100% for example. In the resilience triangle, the loss of service provided is determined by calculating the area of the resilience triangle. So in this case, that would be half the base by the height. So half the base is the time between t0 and t1, multiplied by the height of the triangle, which is the loss of functionality, or delta Q in this case. So in Icarus, we have taken inspiration from Tierney and Bruno's resilience triangle that I just showed in the last slide, and we have adapted it for infrastructure managers to develop the resilience impact score. And this is a new way to classify hazards, specifically for climate change, according to their effect on road resilience, taking into account their impact before, during, and after an event. And so we can calculate the resilience impact score by the area of the resilience triangle as before. In this case, the graph looks slightly different as we have included time for the event to occur, as it may not be an instantaneous event. For example, it could be a flooding event, which takes time to recede before restoration of service can occur. In this case, the base of our triangle is the time from t0 to t2, which is denoted by te, time of the event, plus tr, the recovery time, and the height is the loss of functionality during this time, or QD. In addition, in the calculation of our resilience impact score, the impact of the damage is also included, and this is to encompass the widespread nature of the damage, to account for whether it was just an asset that was affected or an entire network. So what kind of inputs do we use in this equation? Well, we have provided some sample inputs here, but these may be adjusted to suit the network being assessed. So for our event duration, this could be instantaneous. It might be less than 6 hours, less than a day, or greater than a day. So you select 0, 1, 2, or 3, depending on what the event duration might be. Same for recovery. The recovery time, the scale can vary from 0 to 4, depending on whether there's no disruption, or there's disruption that's greater than a month. The impact on service, again, can vary from 0 to 3, depending on whether there was no damage at all or whether there was a large amount of damage. And finally, the scale of the impact can range from an object or asset all the way to a network or multimodal scale. And so the resilience impact score is calculated based on the impact of the hazard or the event on the asset. The higher the score, the greater the impact on the asset, the greater the loss of service, and the higher the impact on the system's resilience. So the higher the score, the higher the impact on the system's resilience. So let's take a look at this in operation. How does this calculation work? So first we'll start with the type of asset that we're interested in and the climate impact driver and the event. And these are just to provide information on what you are assessing. So in this case, in the first example here, I want to assess the impact of a cold spell on my road infrastructure, and this is an extreme event. In my theoretical event here, my cold spell, it's going to last for a duration of greater than 1 day, so I've given it a score of 3. And the minimum service level is going to be restored in less than a week. So we've less than a week's disruption here, which results in a score of 2. In the next column, we choose the factors affecting functionality. So I've decided that there's only a small amount of damage, so we give it a score of 1, but because it's a cold spell, it's going to affect my entire network, which gives it a score of 3. When I do my calculation, multiply my time by my factors affecting functionality, we end up with a score of 7.5. The next example is for a landslide. Okay, so again, we have a similar calculation where my event duration is instant. It's over quite quickly. However, it takes a little bit longer to recover from it. It takes less than a month. There is a medium amount of damage, but it's at an object level, so it's localized, and this results in a small score of 3. Finally, we have an example of a tropical cyclone which affects my entire road network. This is an extreme event. Now, the event lasts less than a day, so I give it a score of 2. It takes greater than a month to restore full service, or for minimum service to be restored. So that results in a score of 4 here. It has caused quite large damage at a widespread level, at multimodal level, and so that gives us a score of 36. So we end up with a loss of resilience of 36 for the tropical cyclone, compared to just 3 for the landslide and 7.5 for the cold spell. So in this way, you can compare the impact of different climate impact drivers on your infrastructure and determine how they would affect the resilience in each case. It is important to note that the resilience impact score is a relative value and not an absolute value, but it can be used to help determine which climate impact factors are going to affect our infrastructure the most. So when can we use it? So it can be used to identify high impact climate events which cause disruption to your network. It can also be used to compare impacts of different events on assets and help in decision-making processes. If higher scores are achieved, then adaptation options should be considered to increase asset resilience. Note that a review of KPIs and/or impact chains may also be useful in determining the impact an event could have on an asset. And that's all. I would like to thank you for watching our video, and I hope it has helped you to understand climate change adaptation a little more. I want to help you to measure the resilience of your infrastructure and identify which assets or which climate impact drivers will be the most critical for your network and your organization. Please follow the link below or scan the QR code to find out more information in relation to this project. Go to the resources section of the ACRES website, and in particular deliverables 2.1 and 3.1, which are related to the content of this video. Thank you.